Again, this is part 2 now. We have found the equivalent resistance of the circuit, and now we're going to go back and see what statements we can make about the voltage drops and the current flowing through the different resistors in our circuit. Okay, so we found that the equivalent resistance of this whole entire circuit is 386.8 ohms, and this is hooked up to a 12-volt battery. Hopefully you now have worked with Ohm's law enough where you're hearing I've got volts and I've got resistance. I can probably go and find something, right? So consider V equals IR. Ohm's law, this will be your friend when we're doing circuits. We got V, we got R, we can solve for I. So taking V divided by R, which will equal 12 divided by 386.8 will equal I, our current, which turns out to be 0.031 amps, or as some electrical engineering types would call it, 31 milliamps. Good number to write down, very useful for our circuit. Okay, so we've got 31 milliamps flowing through that one equivalent resistor. So now if we step back one slide, we said that we have 31 milliamps flowing through our circuit. Well, that 31 milliamps is going to have to go through that 200 ohm resistor up there. It's also going to have to go through the 66.8 ohm equivalent resistor and the 120 ohm resistor. It's just like if you're pumping water. If you're pumping 5 gallons per minute through this whole entire circuit, well, we're going to have that 5 gallons flow through here every minute, 5 gallons flow through here, and 5 gallons flow through here. Electrons are conserved, mass is conserved, etc. If for some reason it was flowing faster through one and slower through another, well, then you'd have kind of a buildup, and that's not anything that we've ever noticed. So let's take that 31 milliamps, so 0.031 amps, and see what we can get using that and using our resistors here. So now again, consider Ohm's law. V equals IR. There's only 3 terms in there. So the beautiful thing is that if you know 2 things, then you can figure out another one. So now here in this picture, we have 3 resistances, and we have the same current for every single one. So current, I, times resistance, will equal voltage. Now we can find what's called the voltage drop across each resistor. For this last slide over here, where we had the 12 volt and the 386.8 ohm resistor, it's kind of the trivial case, and we had a 12 volt drop across that one last resistor there. So now in order to find the the voltage drops across each resistor, we're going to take 0.031 amps and multiply by each of the resistances here. So when we do that, we find that by this 200 ohm resistor, we take 200 times 0.031, and we get 6.2 volts. Across this equivalent resistor, that happens to be 66.8 ohms, we get a drop of 2.07 volts. And lastly, multiplying 120 times 0.031 amps, we get 3.72 volts. Just for the fun of it, go and add all 3 of those up. 6.2 plus 2.07 plus 3.72. You know what that equals? 12 volts. Cool result, huh? So we have our 12 volt source over here with this battery, and all the voltage drops across here are going to add up to the voltage that was supplied. Good thing to know. Okay, so now we've got voltages and resistances and current for quite a few of these resistors. Stepping back one, we can write over here that we know that this is 200 ohms. We have 0.031 amps flowing through it, and there's a 6.2 volt drop across it. Quite a lot of information. We can do a similar thing for the 120 ohm resistor as well. We can say that we know that there's also 0.031 amps flowing through it, and that there's a 3.72 volt drop across it. Now for this 110 and 170 ohm resistor, the current is not exactly going to be 0.031 amps. Yes, it's true that right here at this junction, 0.031 amps flows in, splits up to the two resistors, and then comes back together and forms to be 0.031 amps. But as far as how much flows through the 110 and the 170, well, we're going to have to figure that out. The one thing we do know is that we have the same voltage drop across both of them. Before, we said that there's a 2.07 volt drop across that equivalent resistor. So this will be the same for both of these two. So we know that we have 110 ohms right here and 170 ohms right here. And we're going to borrow our number 2.07 volts. So we'll say 2.07 volts on this one and 2.07 volts on this one as well. Again, Ohm's law. Seems like it's getting old, but check it out. If we have V equals IR, and we have both voltage drop and resistance, what do you have? Current. So we take V divided by R to get current. Let's do that for both of them. Taking 2.07 divided by 110 ohms, here we end up with a current through this 110 ohm resistor of 0.019 amps, or 19 milliamps. And then for the 170 ohm resistor, we take 2.07 volts, divide by 170 ohms, and come out with 0.012 amps, or 12 milliamps. Does this seem to make sense? Well, of course. We have 12 milliamps flowing through this really high resistance path right here, 170 ohms, and in this comparatively lower resistance path, 110 ohms, we have quite a bit more, 19 milliamps. Now lastly, for our two remaining resistors, we have 100 ohms and we have 70 ohms. We already have quite a bit of information. We know that between the 100 and 70 ohm resistors, there should be a 2.07 volt drop. We know that between those two also, that 0.012 amps flows. So let's write those things down. We have 0.012 amps here, and we have 0.012 amps here as well. Now you know, of course, hopefully, which equation to use. Ohm's law. V equals IR. What do we have? Resistance, current. This means I and R, so we can find voltage. 100 times 0.012 amps, that's going to yield a 1.2 volt drop. Down here, where we have 70 ohms, and we multiply by 0.012 amps, that's going to give us a 0.84 volt drop. So now we've been able to find the resistance, current, and voltage for each one of these parts. In the last video, we'll look at power.